Podcast for Unit 11. This unit's covering solutions, and this is properties of solutions. For this particular one, we are going to be covering the first two parts here, the solute and solvent, and then solvation. First, we want to talk about water. Water is a simple triatomic molecule. Each OH bond is highly polar because of the oxygen. Okay, so this is what a water molecule looks like. It has two lone pairs of electrons on it. And if you take a look at the periodic table, oxygen sits right next to fluorine on the periodic table, and fluorine is highly electronegative. And so are the other elements around it. So oxygen is very electronegative and steals electrons. So most of the time the electrons from hydrogen are hanging out with oxygen. And this creates a polar bond. A polar bond is essentially like poles on a magnet. There is a positive end and a negative end. With my water molecule here, the oxygen is a slightly negative end and the hydrogen is a slightly positive end. This is the lowercase Greek symbol delta. We've learned about capital delta, which is the triangle. It means change in. The lowercase delta means slightly positive or slightly negative. The bond angle of water is 105 degrees. Probably most of you have been drawing water like this in a straight line with the lone pairs of electrons. But more water is like this. It has a 105 degree angle in between those two hydrogens. Because of this bent shape and the electronegativity of oxygen, the water molecule as a whole is polar. So just like a magnet, it has negative ends and positive ends. In this case, water has one negative end by the oxygen and two positive ends by the hydrogen, and they are ended up being attracted to other water molecules like this. So this is what I was saying before. This is the lowercase Greek symbol delta. We've looked at the capital delta like that, which means change. You saw it for change in temperature back in the thermochemistry unit. This slide's not in your notes because I just want you to take a look at it and understand the basics. So that delta there with the negative sign means it's slightly negative, and then the water molecule has two slightly positive charges on the two hydrogens. Okay, so it's because of these differences why water is polar. Now, these negative ends, like I was saying here, here we go. These negative ends get attracted to the positive ends of other water molecules. And this is what we call hydrogen bonding. And you really don't need to know much about hydrogen bonding. You really mainly just need to focus on your covalent, ionic, and metallic bonds. But it's some of these special properties of water that give it its special properties, specifically its high surface tension and low vapor pressure. Perhaps in junior high or elementary school you might have done an experiment to see how many drops of water you can get on a penny, and it's usually more than you think, because here on the penny, when you start to put drops of water on it, it becomes rounded on top. And that's the high surface tension there. That's what allows you to get so many drops of water on it. You can also do the same with a water glass. If you're careful, fill it all the way up to the top, and you can actually fill it above the top of the glass if you're really careful. Now, ice is formed because of this hydrogen bonding. Ice has a honeycomb structure. I don't have the animation here for you guys to see, but this is a representation of it. Okay, liquids have the most kinetic, well, I take that back. Gases have the most kinetic energy. Then liquids now have more kinetic energy than compared to a solid. So as your water molecules are moving around, okay, higher temperatures or higher kinetic energies, they're forming these, and let's change my ink color here so we can see it. They're forming these hydrogen bonds. Okay, that's these here and here. Okay, so that's the negative ends being attracted to the positive ends. Now, when ice forms, okay, water's being turned into a solid. We've lowered the kinetic energy. That means the molecules are moving less. And so these hydrogen bonds can end up staying connected better. And so ice gets this six-sided crystal type shape here. And it kind of forms a honeycomb arrangement, a repeating pattern. If you've ever, let's say, filled up an ice cube tray in the freezer to the top, when you come back after it's all frozen, you might notice that some of the water had spilled over. Or if you've ever put a soda in the freezer and forgotten about it, it usually ends up exploding. And that's because of the ice forming. It's taking up more space in the can and essentially breaks it at the weakest point, which is the top there, and then makes a nice slushy mess in the freezer. Now, your definition of a solution is a homogeneous mixture that is mixed molecule by molecule. Now, homogeneous is a word we haven't had in a while. Okay, way back in the beginning of the first semester. And, you know, it's just a mixture where you can't separate the parts out, as opposed to a heterogeneous mixture where it's much easier to separate the parts out. Now, a solution's made up of two parts. There's the solvent and the solute. So the way you can tell them apart is the solvent is present in the greatest amount. The solvent can be a solid, liquid, or gas, even though it doesn't say it here. So the solvent can be a solid, liquid, or gas, and the solute is what's been dissolved in the solvent, and it too can be a solid, liquid, or gas. You know, we typically think of solutions being formed by having something dissolved in something else, like a spoonful of sugar in a cup of tea. Okay, in that case, your solute would be the sugar, your solvent would be the cup of tea. Now, these things can switch around. Okay, remember the solvent is present in the greatest amount. Okay, so it just depends on percentages. If it's, you know, mostly one thing, then the solvent will be that, and it may shift and the solvent will become something else. An example of a gas solution would be air. Air is approximately 80% nitrogen and 20% oxygen. And yes, there's some other things in there like water vapor and carbon dioxide gas. But if we take a look at like this, my solvent is nitrogen because it's present in the greatest amount, and my solute is oxygen. Solids can also form solutions. These are typically alloys like steel, brass, what's some other alloys? Pewter, okay, where you have multiple metals mixed together. You know, brass is a combination of copper and some other things. Steel is usually a combination of iron and carbon. And so those are also solutions. So we have one thing mixed with another. Now, we also have an aqueous solution, where that's defined as water being the solvent. And we've had aqueous solutions before. Those get abbreviated with the AQ down at the bottom. But aqueous solutions telling you absolutely water would be the solvent. So water dissolves ionic compounds and polar molecules best. Remember, ionic compounds are a metal with a non-metal. Okay? It's been a while since we've talked about ionic compounds. So a metal with a non-metal. It'll also dissolve polar covalent molecules. Essentially, the rule is like dissolves like. What this means is polar compounds dissolve polar compounds, and non-polar compounds dissolve other non-polar compounds. So a question I like to ask students is, why don't oil and water mix? And sometimes they say, well, because the oil is less dense than water. And while that's true in some cases, that's not why they don't mix. It's because the water is polar and oil is nonpolar. Okay, so oil is a nonpolar compound. So those two things, they're not going to mix together. Let's see, some other things that are nonpolar. Gasoline, that's a nonpolar compound, the gas we put in our cars. Water, sometimes we'll put water in a styrofoam cup. Okay, water doesn't dissolve a styrofoam cup. Okay, but water will dissolve, gasoline will dissolve a styrofoam cup because like dissolves like. The other thing that will dissolve a styrofoam cup is acetone. I did this demo in class, and this is something you can try at home, but you need to be careful and do it over the sink. Acetone's found in nail polish remover, so if you have a styrofoam cup, stand over the sink and pour some acetone in it, and it should dissolve it away. The acetone that's generally sold in the stores and nail polish removers has been diluted down, so it might be kind of slow, but it should happen. Or if you go to a beauty supply store, you can get some more concentrated acetone. There's also lots of other polar compounds, but this is just trying to illustrate the differences between the two, between polar and nonpolar, and water is our most common polar compound. So this is an old STAR test question. It says water is a polar solvent, hexane is nonpolar. And then it gives you this table. And it asks, is urea a polar or a nonpolar compound? Well, soluble means that it dissolves. And insoluble means it doesn't dissolve. Okay? So, if we're looking at urea, is it a polar or a nonpolar compound? Well, it dissolves in water, but not in hexane. And so since the rule is like dissolves like, and it tells us up here at the top that water is a polar solvent, then urea must also be polar. And then we ask if naphthalene, which is a component to mothballs, is naphthalene polar or nonpolar? Well, it's soluble in hexane. And hexane, we're told up here, is nonpolar. So naphthalene must also be nonpolar. And then our third question, which substances above illustrates a polar solute in a nonpolar solvent? Okay, so we're looking for a polar solute in a nonpolar solvent. Well, my solvents are water and hexane, and it tells us that hexane's nonpolar. So we're not even going to look at water, we're just looking at the hexane. Now, polar solute in a nonpolar solvent, we would expect it to not dissolve. So I'm looking for things that will not dissolve in hexane, and that would be magnesium chloride and urea. So MgCl2 and then urea as an answer. Alright, now this idea of electrolytes. Electrolytes simply are compounds that conduct electricity in an aqueous solution or the molten state. All ionic compounds are electrolytes. And electrolytes will dissociate into ions, which are also called, these ionic compounds are also called salts. Remember, an ionic compound is a metal with a nonmetal. That's all we really need to know there for the most part. Okay, electrolytes will conduct electricity. They're made by combining a metal with a by using an ionic compound, which is made up of a metal and a nonmetal. So when Gatorade advertises that they have electrolytes in there, all this means really is if they dissolved some salt, some sodium chloride in there, it meets the requirements that it's an electrolyte solution. So it's really not that impressive when you know a little bit of science behind it. Things that do not conduct are called non-electrolytes. Non-electrolytes are molecular materials, and these things do not have ions. So molecular compounds are the same things that have covalent bonds. And those things that have covalent bonds are made up of non-metals only. Okay? And they're not going to conduct electricity because they don't have ions to carry the electrical current. You've got strong electrolytes and weak electrolytes. Strong electrolytes will dissociate nearly 100% into their ions. And then weak electrolytes, only a small fraction will become ions. This depends on the degree of ionization. Okay, so dissociation. So to dissociate is to split apart from something else, and then to ionize is to split into ions. For us, they mean pretty much the same thing. It's just two different ways of saying the same thing. To dissociate is to split apart, and to ionize is to split specifically into ions. Now, here's your classification of electrolytes. In your strong electrolyte category, you have strong acids and strong bases, which we haven't really talked about yet. We're going to talk about those more in the third section. And then your ionic compounds, which I'm just going to remind you yet again, metal with non-metal. Okay, they have ionic bonds. Your weak electrolytes, they're going to conduct electricity a little bit. Those are weak acids and weak bases. And then your non-electrolytes are your molecular compounds, which have covalent bonds, which means they are nonmetals with other nonmetals. Okay. All right, now making a solution is done through the process called solvation, and that's kind of, I think, the tougher thing in this section is there's a lot of words that sound the same. You have solution, solute, solvent, and solvation. And solvation is just the process of making a solution. And what happens here is you have a salt crystal in these pictures, and then surrounded by all these little red and white water molecules. And what's happening is the water molecules are pulling apart the salt crystal, and they're surrounding them and pulling it apart. What's happening here is your salt crystal is made up of Na pluses and Cl minuses, an alternating pattern. And so remember, the hydrogen has the slightly positive end, and so it's being attracted to the Cl minus, and then my oxygen is my slightly negative end, and it's being attracted to the Na plus. And then it ends up encircling them and surrounding them and trapping these molecules apart as they pick them apart and remove them. That's how ionic solids dissolve in water. So it says these ions have been pulled away from the main crystal by the water's polarity, and then they've surrounded by water, and that's when they're considered to be dissolved. Solids will dissolve if the attractive force of the water molecule is stronger than the attractive force of the crystal. So, you know, you've got those Na pluses and Cl minuses being attracted to each other. You also have the polarity of water. And so, you know, if the polarity of water is stronger than this electrostatic bond between sodium and chloride ions, then it will dissolve. The term for when two liquids dissolve in each other is called miscible. This would be like water and alcohol. Okay, those two things will mix completely in each other. But we talked about oil earlier, and oil and water don't mix, and that's because of their different polarities. And when oil and water don't mix, or two liquids don't mix, they're called immiscible. So water doesn't dissolve non-polar molecules like oil because the water molecules can't hold on to them. The water molecules, remember, have those plus charges and the minus charges. Well, things that are nonpolar don't have plus or minus charges on them. So there's nothing for the water to grab onto. And so, you know, they can be called insoluble, but like I said, if it's two liquids that won't mix, it's called immiscible. So oil and water are immiscible in one another. So in order for something to dissolve, the things have to come in contact with each other. The solvent must come in contact with the solute. And you can increase this contact in two ways. You can stir it, or you can increase the surface area by grinding it into a finer powder. There's a reason why in chemistry we usually give you powders instead of big chunks of things to do your experiments with, and that's because they dissolve better and they react faster when they are in smaller pieces. So again, here's just a close-up. This is like a salt crystal dissolving in water, and you can see down here in this region where it's dissolving, and it's very concentrated right there. So again, this is just a close-up. You can see the plus and minuses of the sodium ions and the chloride ions being surrounded by these water molecules picking it apart. So you've got three different types of solutions. You've got saturated, and that means you have the maximum amount of solute dissolved in it at a given temperature. You also have an unsaturated solution, and it can still dissolve more solute if you try and add it. Supersaturated solutions, the solution's holding more solute than it theoretically should. With a saturated solution, sometimes you see some solid that has been undissolved. Okay, that's one way you can tell you have a saturated solution, is if you have undissolved solid in the bottom of your beaker. So, I mean, think about it this way. You can take cold iced tea or cold lemonade and try and add sugar to it, and it's not going to dissolve, no matter how much you stir. And so at that point the solution's saturated. If you can still get more sugar to dissolve in it, it's unsaturated. Now, supersaturated solutions are special solutions that hold more solute than you expect, and it's made by heating the solution and dissolving large amounts of solute and then slowly cooling it down. These solutions are really unstable. They're going to recrystallize with the use of a seed crystal, which is just a piece of the solute. So you add a piece of the seed crystal, or even from shaking it. So if you go, here's a couple of web links that I know you can't click on now, but if you go to like YouTube and you search hot ice, you'll see it's sodium acetate solutions, a supersaturated solution, and you can see some videos of them being made. You're actually going to make one yourself. That's part of what your lab is. In part 4 of your lab, you are going to make a supersaturated solution and see what it's like. There's all sorts of supersaturated solutions that you encounter in your life. Honey is a supersaturated solution. So is candy. Not like chocolate candy, but like hard candy. And it's made by taking some sugar, large amounts of sugar, adding just a little bit of water, and heating it up until all the sugar dissolves. And then you can recrystallize it in the forms that you want. So supersaturated solutions, they're pretty cool. If you do a little search on the web, like I said, you'll find some neat things. All right, now there's factors that affect solubility, and I've actually kind of already mentioned one. Solubility is the amount of a substance that dissolves in a given substance to produce a saturated solution. So essentially, solubility is how much stuff can dissolve in it. Solubility is affected by two things. This is the one I already mentioned. Temperature. It's going to increase the solubility for solids and liquids, or decrease the solubility for things that are gases. So like I was saying earlier, when you're making if you have cold tea and you're trying to stir sugar in it, you don't do a very good job of getting a lot of sugar dissolved if you like really sweet tea. But hot tea will definitely hold more sugar. So sometimes what they do to make like sweet tea that you can sometimes find is they actually warm the water and dissolve the sugar in it and then cool it down. That's also a good way to make lemonade, is to actually start with warm water. You'll get more sugar in it. So that will increase the solubility of solids like sugar and other liquids. If you raise the temperature, that will decrease the solubility for gases. So if I increase the temperature, that decreases the solubility for gases. So if I have two sodas, one warm, one cold, the warm soda is actually going to taste flatter because more of the carbon dioxide has left the soda solution. So if you really like fizzy, bubbly sodas, cold is better. If you increase pressure, and this really should say increase here, if you increase pressure, that typically increases solubility. If you think about pressure as squeezing something, well then you can squeeze more of your solute into a solution. Now this is a solubility graph, and sometimes you'll get ones that are a little more simpler looking. This one does show up on your quizzes and tests, and it's really not as freaky and hard to read as it may look. Down here at the bottom for my x-axis, this is the temperature. For the y-axis, it's grams of solute that can be dissolved in 100 grams of water. And then I have all these different compounds here, like Ki, NaNO3, things like that. And then it's telling you the solid line is for solids, and the dashed line, that represents gases. So you can see what I was saying on the last slide. As you increase the temperature, the solubility of these gases actually goes down. You can dissolve less. So if we read this side here, how many grams of KNO3 can dissolve in 100 grams of water at 50 degrees Celsius? Well, first you have to find KNO3 on the chart. Okay, here's KNO3. And we go to 50 degrees Celsius, down here at the bottom, 50 degrees Celsius, and we follow that line up until we hit the KNO3 line. And then, let's see if I can get this straight enough, and then we take it across and read the temperature, or read the grams. And so there I get about 85 grams in there. So that's how many grams of solute can go in 100 grams of water. Okay, I can get 85 grams of KNO3 in 100 grams of water. If I had 200 grams of water, H2O, okay, and I wanted to know how much KNO3 I can get in it, well, since the chart's for 100, but now I doubled my water, I'm actually going to double my KNO3. If I had half as much water, if I only had 50 grams of water, I could only hold half as much KNO3. Okay, so it's pretty easy to do. As long as you read the question closely and make sure you understand what it's asking there. So let's look at the next question. How many grams of Ki dissolve in 100 grams of water at 10 degrees Celsius? So here's my Ki up here in the corner. I want 10 degrees Celsius down here at the bottom. Follow the line. 10 degrees Celsius. Okay. And then take it across. And so that's 135 grams of Ki in. Now remember, this chart is for 100 grams of water. But we said 200 grams of water. So again, I would just double it, and so that's 270 grams of Ki. And you know, your numbers may vary a bit. You may thought it looked like 134 or 136. That's okay. You know, it's a little imprecise on the chart, but as long as we have close to the same answer, you're good. Alright, one last one here. If 150 grams of KNO3 are mixed with 100 grams of water at 60 degrees Celsius, how much will not dissolve? Okay, so here's my KNO3 again. I'm at 60 degrees Celsius. Get down here, 60 degrees Celsius, follow the line, better than I am. Boom, up here. across. Alright, so I can get 110 grams of KNO3 in there. But I mixed in 150 grams, and it's asking how much doesn't dissolve. Well, 110 grams does dissolve. That does dissolve in. And I want to know how much doesn't dissolve. Well, it's just a simple subtraction. 150 minus 110 is 40 grams of KNO3. Okay, so 40 grams doesn't dissolve. That's my answer. So, if you were working with a solution like this, you would actually have solid KNO3 in your beaker. It would not matter how much you stirred. It would not dissolve. The only way you could get it to dissolve is to actually increase the temperature or increase the pressure, okay? But stirring it or grinding it wouldn't actually change how much of the KNO3 dissolves, because solubility is temperature dependent, okay? So really you got to change that temperature there in order to get more in. Alright, so at the bottom of your page I want 6 sentences total, 3 things you learned, 2 things you want to know more about, and 1 thing you'll never forget. Okay, so instead of a summary, because this was a big section, alright, 3 things you learned, 2 things you want to know more about, 1 thing you'll never forget. And these need to be in sentence form, except for number 2, questions are okay. Alright, if you want to write me a question, that's alright. Okay, so just fill that in at the bottom of your page, and then take a moment and fill in your unit organizer for solute and solvent, okay, for this one, and solvation.